Awesome. How are you guys doing?
Made it.
We're so close to the end, right? Even if you're not doing well, just hold on a little longer. All right, I need to get a few things together here before we start. And we'll get going in a minute. Okay. Before I get started, does anybody have any sort of general questions or bookkeeping they want to go over before we jump into things? Or just let me have at it. Well, if there are no questions, then we'll just jump into it. Again, if you don't mind, just for the sake of the recording, if you'll keep yourself muted, unless you have a question or something, I want to jump in with a question. That will make my life a lot easier. So let me share my screen and put my computer into tablet mode so I can write. Okay, so this is the exam review that I posted. We're going to go through it in a minute. But before we go through the actual exam review, I want to focus on a couple of big picture ideas and try to kind of organize our thoughts about all the stuff we've covered over the last 3 weeks, because as I'm sure most of you are aware at this point, things are getting a little bit more technical and a little bit more involved. These are not easy topics here at the end. So to kind of keep things straight, one thing I like to do before this exam is give you guys essentially a decision tree for you to figure out what type of problem you're dealing with on the exam. This is an issue that I see students run into over the last few weeks. When you're working on the homework, you know exactly which section you're working on, right? So you know when you're in section 8.1, it's a confidence interval for the mean with sigma known. But when you're working in 8.2, it's a confidence interval for the mean with sigma unknown. But on the exam, I don't tell you which type of problem it is explicitly. So what are the cues that we're looking for to make that type of a determination? And this is something that hopefully will help you all on the exam. So I'm going to kind of do that up here above this. If this will allow me to write, come on, let me go up a little higher. Okay, let me start writing up here so there's more room. All right. So this is going to be, let me do this in darker pen. This is going to be our, ooh, that's ugly. Our decision tree. And again, it's just, the whole point of this is to decide what type of problem we're dealing with. And of course, it's trying to scroll me down. I want to move this up so I have more room to write. Come on, let me move it up. Okay, good enough. Hopefully that'll be enough room. I'll try to write tiny. So basically the question is, what type of problem on the exam are we encountering? So what type of problem? You see a big word problem. How do we know what to do? So basically there are 3 different types of problems that we've encountered from the 3 different chapters. So this exam is going to cover chapters 7, 8, and the portion of chapter 9 that we've covered. There will be a little bit more of chapter 9 after this exam, but so basically everything up through 9.3. So all of chapter 7 that we talked about, all of chapter 8, and chapter 9 up through 9.3. So each one of them kind of had a different type of problem associated with them. So I'm going to do 3 little branches here for each of those 3 types of problems. The chapter 7 stuff was all about the normal distribution. So in this case, we were just dealing with the normal distribution. And we were asked questions along the lines of basically, animals of, this certain species of animal, their weights are normally distributed with a mean of this and a standard deviation of that. What's the probability that a randomly selected dog is between, 38 pounds and 47 pounds or something like that? So the key word you're looking for here is they will explicitly be asking you for a probability. They will say, what is the probability of ... some event? They want you to give them the probability. We basically did this in kind of 2 subcategories under this. I'll break it up into situations where we were dealing with like a single individual. So single individual versus a question about a sample mean. And what I mean by this is back in section 7.1 and 7.2, the problems that we had were basically, what is the probability that a dog, a single individual, has a weight between 38 and 45 pounds or something like that. Whereas in 7.3, when we started doing sampling distributions, it would ask a question about the probability of a mean. So what is the probability that the average weight of this group of 30 dogs was between 38 pounds and 45 pounds or something like that? So instead of asking about a single individual, they ask, what's the probability that a sample mean falls into some range of values? And so this is basically sections 7.1 and 7.2, where this corresponds to section 7.3, the sampling distribution. In these cases, right, the mean that you use is going to be mu. The standard deviation, we'll do an example of one of these on this exam review. So we'll see this in a minute. The standard deviation is just sigma. And over here, we're dealing with a sampling distribution. So the mean is still mu, but the standard deviation is now what we normally call the standard error, where we have to take sigma and divide by the square root of n. But basically, otherwise, we're doing these problems either on the calculator using Normalcdf, so, or we're using table A2. So basically, we use either table A2 or, and let me just write the way that we get there. You do second vars to get to your list of distributions, right? This is distr or something on the calculator. And then you go to Normalcdf. And you use this in both cases. The only difference is when you do this, it'll ask for a mean and a standard deviation. Here, you just use the normal mean and standard deviation that are given, whereas in this case, you'll input for the standard deviation sigma over the square root of n in the calculator. So this is the idea. And again, we'll do an example of one of these, but this is one type of problem that we did. These were ones basically just finding the area under the curve. Right? These all just boil down to finding area under the normal distribution curve.
That Normalcdf, that's normal dist in Excel, right?
In Excel, yeah, it's equals norm.dist. And I'll try to remember to, yeah, let me write that down as well. The Excel command is equals norm.dist. And I'll try to do it in Excel when we get to that problem on the actual exam here. So if you want to use Excel, you absolutely can. I can't remember if I showed how to do that much in my videos. I think I mostly concentrated on either using the table or using the calculator. But you're welcome to use Excel as well. So, okay, so this was basically the chapter 7 stuff. The next branch of our types of problems is chapter 8, where we did confidence intervals. And they're pretty easy to recognize because they literally will explicitly ask you to construct a confidence interval. So the keyword we're looking for is literally the word confidence interval, or just even the word confidence, basically. If you see the word confidence, you're dealing with a confidence interval. And so this was, again, chapter 8, and we broke this into kind of 2 subcategories, and hopefully I will do this in such a way that I have some room. We had confidence intervals for the mean, and we also had confidence intervals for a population proportion. And again, if we want to kind of come down here and talk about what keywords can we use to distinguish each. When we were trying to find a confidence interval, the goal was to basically predict the mean. And the words that they'd explicitly use were either the mean or the average. These are the types of words you would expect to see. So words like mean or average. Whereas if you were dealing with a population proportion, the keywords, sometimes they would say portion or proportion or percentage. So we'll use this, we'll practice using this again, this little decision tree that I'm giving you. We'll practice using it in a minute when we actually do some problems. So there were 3 total confidence intervals that we did, not just 2, because there were 2 sort of subcategories of confidence intervals for the mean. We had confidence intervals for the mean where sigma was known, and we had confidence intervals for the mean where sigma was unknown. So we can actually branch down further here and have the sigma known case and the sigma unknown case. But really, it's that sigma was unknown, but we still did know a standard deviation, and it was S. So I'm going to instead call it S is known. So basically, a standard deviation is going to be given in these problems. It's just a matter of a question of whether that standard deviation is the population standard deviation sigma or just the sample standard deviation S. So we have to be able to distinguish between those, and distinguishing between these essentially just requires reading comprehension skills. So right here, there's no special keywords. This just requires reading comprehension. And it's going to be something that, again, you'll want to practice a little bit. We'll do it on this exam to figure out what type of problem we're dealing with. The sigma known stuff was section 8.1. When S was known, that was section 8.2. And when it was the population proportion, that was section 8.3. In general, to answer these problems, we still needed those, either the probability distribution tables or a calculator. Technically, you could also kind of answer some of these in Excel using some of these same commands over here, the normal distribution or a t-distribution. But basically, in this one, we can use table A2 or table A3. Both are fair game. And similarly over here, so let me say it this way. Why can I use both tables? This is something that people often mix up, is on these problems, when do we use a normal distribution and when do we use a t-distribution? So let me make that totally clear as well. If we know sigma, that means we're dealing with a normal distribution. But if we know S, the sample standard deviation instead, then we have to use a t-distribution instead. And that precludes us from using table A2. So the table A2, I have them over here. Table A2 is the cumulative normal distribution. It only applies when we have normal distributions, whereas table A3 down here, this one is the t-distribution. So it will apply in the cases where we're dealing with the t-distribution, but it actually also is helpful, right? If we want the quick way to find a confidence level, for example, even if we have a normal distribution, we can just use this bottom row. So this one can really be used for both normal distributions and t-distributions. But these ones up here can only be used for normal distributions. So with that in mind, looking at all of these, this one is oops, let's go back to writing with the pen. This one is a normal distribution. This one is a t-distribution. And this one requires also a normal distribution. So basically, the only time we use a t-distribution is whenever we're dealing with S. T and S essentially go together. If we've got sigma, we've got a normal distribution, and also all the problems that deal with population proportions involve a normal distribution as well. So it's just this one pairing, S and T go together. And because of that, on this one I can use, on this one I can use A2 or A3, but on this one I can only use table A3. This one I can use A2 or A3 because again, table A3 I can use that bottom row for a normal distribution. But this is the one case where there's a restriction. I cannot use table A2 if I'm dealing with a t-distribution. The calculator commands for these are basically, you hit the, oh, come on now. I knew this was going to happen. Let me move this further from there just so I can make this easier to write. Hopefully it'll stop doing that. Hopefully my computer doesn't freeze. Okay, come on now. My computer is temporarily frozen. It's thinking too hard, trying to move all that text at once. Come on. Okay, while I'm waiting for it to unfreeze, whoa, there it goes. So all I'm trying to do is give you the commands you can use on the calculator for this. So you hit the stat button. You go to the list of tests. And in fact, let me give a little bit more room here. So we're going to hit, in this case, stat. Oh, come on now. Really? That made it even worse. Okay. I'm just going to live with this. I don't know what's going on. So stat, the list of tests, and this one is a Z interval. So on the calculator, you use Z interval for this type of problem. For this one, it's similar. You hit stat, then test, but this one is a T interval. And this one is a 1-prop Z int. So again, int or interval whenever we're dealing with a confidence interval. So those are the calculator commands you would use for each of those respectively. And then we move on to chapter 9. So chapter 9 was all the hypothesis tests. And luckily we only have 2 so far. But on the final exam, we'll update this decision tree because there are going to be a total of 6 different hypothesis tests when the final exam rolls around. The key word here is going to be significance. They'll always talk about a significance level. Unlike in a confidence interval, where they explicitly tell you to construct a confidence interval, over here they'll be asking some question, right? All the hypothesis tests pose some question that we have to essentially answer yes or no. Like, is there enough evidence to support this idea, yes or no? But one thing that will always show up as we make our determination of whether there's enough evidence is the idea of a significance level. So if you see the word significance, that's your indication that we're dealing with the hypothesis test. But otherwise, and I should just make it totally clear, significance level. Only problems that talk about significance levels are hypothesis tests. And they will ask some sort of question that we have to answer, yes or no. So far, we've only done hypothesis tests for the mean, so that simplifies things. We will do them for population proportion as well, and some other tweaks on this concept. But we had 2 of them so far. So we had, similar to hypothesis tests, we basically had some where sigma was known and some where S was known. So we have our sigma known cases and our sigma unknown, where instead we know S. So S is known instead. These were section 9.2 and these were section 9.3. Similarly, these ones involved a normal distribution, so we're dealing with like a z-score, and these ones were a t-distribution, so we're dealing with like a t-score. So just to make that totally clear, normal and z t-distribution, that goes with a t-score. So same as before, over here we're allowed to use tables A2 or A3 if they're helpful to us, whereas in this case, only table A3 is allowed. And the calculator commands are similar to the ones we had over here. We hit stat and tests, but instead of looking things for with the word interval in them, we're looking for things with the word test in them. And so far we have a z test and a t test in the calculator. So there's our full decision tree. So far, at least, this is what we've got. This is the information that we have. Any questions about this? It'll hopefully make more sense once we actually start applying it to problems down below when we start doing the review. But are there any general questions about this? Okay. Well, if one comes up, don't hesitate to chime in and ask it. Let me just make sure I've got everything we need. Okay. So let's do the exam review. I'll start again. Normally, I'd encourage you to skip the multiple choice and come to them at the end. But for now, for this, let's just do them first. So problem number 1 says, find the approximate critical value z sub alpha over 2 needed to construct a 99.5% confidence interval. And there's a hard way to do this and an easy way to do this. And I would encourage you all to please do the easy way. We just need to look this up over in table A3. So if I go find table A3, it lists a bunch of common confidence levels. And one of those common ones happens to be 99.5. So wherever it is, here's table A3. Come down to the bottom, look through the list of confidence levels, and sure enough, there we go. Our confidence level is 99.5. The corresponding z-score, which is the critical value, is 2.807 in this case. So if I had to round that to 2 decimals, because I think our answers are 2 decimals, I'd do 2.81. So coming back over here, we're looking for 2.81. And sure enough, answer A is 2.81. So, geez Louise. I think what's going on is my pages didn't get locked. Let me just zoom out and try to lock all these pages. I don't know what's going on here. Give me just a moment. Here, let me lock that in place and maybe it'll stop acting so weird. Okay, see if that fixes it. Okay, sorry. So 2.81, answer A. There we go. Okay, and the only difference is if instead I'd asked for a critical value that involved a t-score instead, we would also need degrees of freedom, and we would have just used a different row. So if I said find the approximate critical value t sub alpha over 2 with a sample size of 31 needed to construct a 99.5% confidence interval, all we'd have to do is come down to the table, same as before, so same confidence level, but because I said degrees of freedom was 31 and it's a t-score instead, or sorry, I said sample size was 31. So degrees of freedom was 1 less than that. We'd look at row 30 if the degrees of freedom was 30. So if n equals 31, let me just write down what I'm trying to say. Degrees of freedom would be 30. And we'd use this row, and I would just go find that value. You'd use that number instead. But that would be if we were using a t-score instead of a z-score. So just a reminder for how to use this table. We aren't actually doing that here, so I'll erase it, but that would be the idea. Okay. Problem number 2. A hypothesis test for a population mean, mu, yields a test statistic of t equals 0.279 and a p-value of p equals 0.089. Should you reject H0 at the alpha equals 0.1 level of significance? Well, in this case, there's a bunch of extra information given. We don't actually need the test statistic here. We can ignore that entirely and get rid of it. All we need to do to decide whether or not to reject the null hypothesis when we're doing the p-value method is compare the p-value to alpha. And if p is less than alpha, reject H0. And so for us, in this case, 0.089 is indeed less than 0.10. So we should reject the null hypothesis. The answer is yes. Problem number 3 says the point estimate and 99% confidence interval for a population proportion P are found to be P hat equals 0.581 or 83120 and yada, 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 these numbers respectively. So fill in the blanks. What this tells us is we are a certain percent confident that the population mean is between two numbers. And in this case, because it's a 99% confidence interval, we are 99% confident that the population, and I said mean, but I think I said proportion. That was just a typo. So this should say, let's just switch this one to mean. But we're 99% confident that the population mean is between the two values that are given. That's basically, if you just had to interpret this into words, again, it's going to be part A. And I just didn't mean to have that typo, talking about proportion in one part and mean in another part. That wasn't meant to be a trick question. So in that case, again, the confidence level tells us how confident we are that our answer is right. And then the actual bounds of the confidence interval are the interval where we think whatever we're trying to find, whatever we're trying to predict, in this case, a population mean, we think it lives between those two numbers. So that is the idea. Problem number 4. A test of the null hypothesis, which states that mu is equal to 56 versus a null or an alternate hypothesis that mu is less than 56, is performed using a significance level of 0.05. The p-value is 0.174. If the true value of mu is 56, does the conclusion result in a type 1 error, a type 2 error, or a correct decision? So this problem has a lot to hold in our mind at once. Remember, we need to figure out, first we need to figure out what conclusion, right? It says, does the conclusion result in one of these? What is the conclusion even? So let's start with that. If we can figure out what the conclusion is, then we can decide if that conclusion is the correct decision or not. And if not, is it some type, which of the two types of error is it? So let's think about this. What it's essentially saying is, up here, we assumed that mu is equal to 56 according to our null hypothesis. There's maybe some evidence that mu is in fact less than 56. We run through everything and it turns out that the p-value is 0.174. So basically we found that p equals 0.174. Are we going to reject the null hypothesis or not? Well, because our significance level is 0.05, we want to check to see if the p-value is less than alpha, which is 0.05. Is this p-value less than alpha? No. So we don't reject H0. That would be the conclusion. So when it talks about the conclusion, we're trying to decide whether or not we've rejected H naught. Based on this p-value and this value of alpha, we're not going to reject the null hypothesis. We did not get particularly strong evidence, right? We only reject the null hypothesis when p is less than alpha. If p is greater than alpha, as we saw here, we don't reject the null hypothesis. Okay, so that's one piece to keep in our mind. We've decided that we are not rejecting the null hypothesis. If I had to come translate that back into plain English, what we're not rejecting is the idea that our average value is 56. So we're not rejecting the idea that mu could definitely possibly be 56. Now, if the true value of mu is in fact 56, did we make the right decision or did we screw up? In this case, we made the correct decision. We decided not to reject the null hypothesis, which means we decided not to reject the idea that mu equals 56. We're saying it's totally plausible that mu could be 56. And it turns out the true value of mu is indeed 56. So it turns out our conclusion was the correct conclusion to draw. Mu may in fact be 56. So there is our correct decision. Any questions on that one? That one is, I think, probably the trickiest multiple choice here. Okay, we'll come back and maybe we can touch on this again at the end on just like what is a type 1 error versus type 2 error. Maybe at the end of the exam if people still have questions about that. So if you have questions, again, don't hesitate to reach out or pipe up sometime during this review. Okay, problem number 5. A new organic pest formula is being tested on potato plants to see whether it can reduce the level of potato beetle infestation. The mean number of beetles per untreated plant is 5. It is hoped that the new formula may reduce this infestation rate. State the appropriate null and alternate hypothesis. Well, one thing I need to keep in mind that can help narrow these down is that the null hypothesis always, always, always has an equal sign. So I can immediately rule out A and B. It has to be one of these two because the null hypothesis always uses an equal sign. In this case, it's saying, so the idea is that if the null hypothesis was true, it would mean that nothing had changed, that this new formula doesn't help at all, right? So basically, if the untreated plants have 5 bugs on them and this new product doesn't help at all, then the null hypothesis says that the average number of bugs on the treated plants should still be equal to 5%. And that's what it's, or 5 bugs. So that's what this is saying. The hope, however, and presumably there is some evidence to back this up, is that this new pest control formula will reduce the level of potato beetle infestation, which means we would expect to see, if it's effective, we would expect to see fewer than 5 bugs on each plant. And so what that tells me is the alternate hypothesis, which the evidence is supposed to support, should be that mu is less than 5. And therefore, the correct answer is D. If it had simply said, we're hoping that this pest control formula changes the number of bugs on each plant, not specifying that it should go down, maybe it also will go up. Maybe we're putting, spraying their favorite scent onto the plants and attracting them, who knows? In that case, we would use the not equal sign, but because they specified that we were hoping to reduce the potato beetle infestation, that the average value should go down and become less than 5, that is why we selected D. Problem number 6, a garden supplier claims that its new variety of giant tomato produces fruit with a mean weight of 44 ounces. A test is made of mu equals 44 for the null hypothesis versus a null hypothesis that mu is not equal to 44. The null hypothesis is not rejected. State the appropriate conclusion. So this is really a wording question. Basically, we said the null hypothesis is that they do have 44 ounces of tomatoes. The alternate hypothesis is that they don't. And the evidence led to us being unable to reject the null hypothesis. The null hypothesis is not rejected. What that means when we don't reject the null hypothesis, we aren't saying that the null hypothesis is true. we're simply saying it could be true. Essentially what we're saying is we didn't have enough evidence to verifiably say that it's false. So we're not saying it's true, we're saying it may be true, right? And that's kind of the idea. Same thing in a criminal trial, right? You don't proclaim the defendant innocent, you just say not guilty. They may have done it, but there wasn't enough evidence to convict. So we need to find wording that basically gives that same idea. And in this case, if you read through them, Part B is too certain of itself. The new variety of giant tomato plants produces fruit with a mean weight of 44 ounces. We aren't sure that that's true. We just don't have enough to disprove that. So it's not that. There's no weird negatives in here. We certainly didn't say anything about less than. In this case, it's answer A again. The new variety of giant tomato plants may produce fruit with a mean weight of 44 ounces. So it's not guaranteed, but the null hypothesis might be true. And this is the phrasing that states that idea. Okay, problem number 7. In a survey of 447 registered voters, 157 of them wish to see Mayor Quimby lose his next election. And I think oh yeah, no, we're good. The Quimby campaign claims that no more than 27% of registered voters wish to see her defeated. Does the 98% confidence interval for the proportion given here, 0.299 up to 0.404, support this claim? And the answer in this case is basically no. So the idea is we're pretty sure, according to our confidence interval, we're 98% sure that the proportion of people that want to see her defeated, right, that the proportion of people that want to vote against this person is between basically 29.9% and 40.4%. These are those same percentages just written as proportions. So basically, we're 98% sure that the proportion of people that wish to see her defeated is between about 0.3 and 0.4-ish. In this case, both those numbers, that whole range is above 27%. So there is not evidence to support their claim in this case. If their number was, somewhere in this range, or if their number was, no more than 45%, well, certainly these numbers are both below 45%, then they would have a claim that would be supported by the evidence, but not at 27%. Are there any questions about that one? Okay. Problem number 8. A 95% confidence interval for a sample size n equals 36 has a margin of error of m equals 1.28. If all else stays the same, but we instead compute a 99% confidence interval, what will happen to the margin of error? So I mentioned this in the video when we were introducing confidence intervals, where you can almost think of them as kind of essentially a target. And if we want to go from being 95% sure we can hit the target up to 99% sure that we can hit the target without changing anything else, what should we do to the target? Well, if we make the target bigger, it's easier to hit. We'll be more confident that we can hit it. So we need to make the target bigger. In this case, making the target bigger corresponds to increasing the margin of error, right? Increasing the size of the interval that we're using, that we're kind of throwing darts at, if you want to think about it. So that is the idea here. If we want to be more confident and we can't increase our sample size, then what we do have to do is increase our margin of error, increase the size of the interval that we want to use. So that tells me that the value of m will increase b. Problem 9, similar setup. A 95% confidence interval for a sample of size n equals 36 has a margin of error of m equals 1.28. If all else stays the same, but we instead are able to take additional samples so that n is equal to 50, what would happen to the margin of error? So what happens to the margin of error if we can increase our sample size? We talked about this at the same time in that same video. in general, the easiest way to think about it is more or less common sense. Is taking a bigger sample a good thing or a bad thing? Should taking a bigger sample help you zero in on the value you're looking for and give you better results, or what is it going to give you worse results? Hopefully it's intuitive to people that taking a bigger sample should yield better results. And in the context of a confidence interval, better results means that we are more zeroed in on the correct answer. Basically, our interval has shrunk. So in this case, we would expect the margin of error, M, to decrease. We are more zeroed in. Another way to see this is just mathematically. The formula for the margin of error in all of these different problems, what we call M, is basically we take the, if you remember, it's, I think, step 4 in our confidence interval process. We compute the margin of error, and it's always the critical value times the standard error. So for example, in like 8.1, it was z sub alpha over 2 times sigma over the square root of n. And in the section after that, it was t sub alpha over 2 times s over the square root of n, and so on. But even mathematically, it's hopefully kind of obvious. If I increase the value of n, n shows up in the denominator down here. So if I make the denominator of this fraction larger, the overall number gets smaller, right? If I look at the number 1 over 1 and compare it to the number 1 over 2 and compare that to the number 1 over 3 and that to the number 1 over 4, even though the denominators are getting bigger, the overall numbers are getting successively smaller. So by increasing the value of n, the overall number here, this fraction, will actually decrease, and therefore m will also decrease. In the last problem, in a survey of 302 registered voters, 167 of them wish to see Mayor Quimby lose his next election. Find a point estimate for the proportion of registered voters who wish to see Mayor Quimby defeated. And in this case, our point estimate, that's just our best guess given the information available. In this case, it's a proportion, and the proportion is going to be 167 out of 302. And so we can just type that into a calculator real quickly. I think I've got one up here. Let me turn this on. And we just do 167 divided by 302. Any calculator will work for this. It doesn't have to be a graphing one. And it looks like it's about 0.55 something. So 0.553 is the closest number that we've got here. So the answer is D, 0.553. If I had to guess one number based on this information, it's that about 55.3% of voters wish to see this guy lose his next election. So that's the idea. Any questions on any of these multiple choice problems? I feel like I'm fumbling a little bit. I apologize. I had my second COVID shot today. I'm just a little foggy. I'm feeling fine, but I'm just slightly out of it. So hopefully it's not affecting this too badly. Okay. Problem 11. Okay, so in a simple random sample of 78 registered voters, 56 said they voted in the last election. We want to construct a 96% confidence interval for the proportion of all registered voters that voted in the last election. So first things first, let's imagine that we're trying to use our giant table that we generated up here. First question is basically, which chapter is this problem from? Which type is it? And hopefully it's clear if we read this that it says, what do we got? Here's our keyword, confidence interval. We want to construct a confidence interval. So there's our keyword, confidence. We're doing a confidence interval. We've narrowed it down to this branch of our tree diagram. So it's going to be one of these three things down here, 8.1, 8.2, or 8.3. So how do we narrow it down further? Well, the next question to ask, here, actually, let me go back up to here. The next question to ask is, are we dealing with a mean or a population proportion? So I'm looking for keywords like mean or average. Am I trying to predict a mean or an average, or am I trying to predict a proportion, a portion, or a percentage? And if we come back down here, Sure enough, here's our keyword. Right here, we are aiming to predict a proportion, the proportion of registered voters that voted in the last election. And that's enough to narrow it down, in this case, to section 8.3. So this is a section 8.3 problem. I just want to say right now, to make it totally clear, you're pretty much going to be guaranteed, just to make it easier on you, you're pretty much guaranteed to have like one of each of these types of problems on the exam. One normal distribution one confidence interval, one hypothesis test. They're all going to show up. But I won't guarantee you, because we did section 8.3 on the review, that it's also going to be 8.3 on the real exam. It might be, but it could also just as easily be one of these. So make sure the real exam will look a lot like this, but it won't be identical. That's all I'm trying to say. But you can assume that there will be at least one of each of these types of problems on there. Okay, so once we've narrowed it down to section 8.3, here's our normal 5-step process, right? The way that I listed it out in the videos, which I know is not exactly the way that Alex always wants you to do it, but I think it's the easier way, and I would encourage you again to follow those steps. Step 1 is always to give the point estimate. And so in this case, when we're dealing with a proportion, and we want to find the proportion instead of the mean, the notation for that is p with a little hat over it. And it's equal to x over n. It's essentially what we just did right here in problem number 10. We're doing that as part 1 of this problem. So in this case, how many out of how many voted in the last election, right? We're trying to construct a confidence interval. In our sample, we sampled 78 people and 56 said they voted in the last election. We're trying to use that to kind of extrapolate and figure out what percentage of all registered voters voted in the last election. So our point estimate is the best guess based on the information available to us. And in the information available to us, 56 out of 78 voted. So that's our proportion, 56 out of 78. Can do that on the calculator again here, or any calculator. And so 56 divided by 78 gives me 0.717, was that what it was? 718, I think it rounded up to. Yeah, 7179. So about 0.718. I'll do 3 decimals here. I also want to give now, next for step 2, give the critical value. In fact, let me see if I can do this. There we go. Can have them on the screen at the same time. So the next step is to give the critical value. And this one's a little bit tricky. Remember the idea behind these types of problems. I'm going to draw a picture over here. And again, I'd encourage you, whenever possible, to get in the habit of drawing these pictures. If you've already done the review, you see that I make you do it in a couple places anyways. But it really is, in my mind, kind of helpful. So this is the distribution of all population proportions that we could have conceivably gotten. Right? We took a particular sample of this group of 78 people and we got 0.718. Our falls somewhere on here. But if we'd taken a sample of a different 78 people, we would have gotten a different proportion. We probably wouldn't have gotten 56 out of 78. And if I did a sample of a different 78 voters, I would have gotten yet a third proportion. So this is the distribution of all the possible proportions. We're trying to figure out the true average proportion. So we're trying to figure out this value sitting right at the actual center. We'll call that P. We aren't totally sure what that value is, but I'm 96% sure that our result fell somewhere between here and here, where the area that's inside of here is now 0.96. Right, so basically I'm saying 96% of the areas inside here. This is 96% of all the possible values of p hat, where p hat could have landed. So I'm not sure where our p hat landed. It could have landed right on top of the p. It could have landed over here and have been in above the true average or below the true average. I'm just pretty sure it's not out here. It could be, but it really only has a 4% chance of landing in one of these places, where it has a 96% chance of landing in this region that I've shaded red. And so that's kind of the idea. We want to build our confidence interval with that idea in mind. The critical value is the value that falls right here. It's the z-score or t-score. And in this case, because we're dealing with a proportion, a population proportion, we are going to use a normal distribution. This is going to be a z-score. So it's going to be z sub alpha over 2. That is the z-score that I want. Because my hope is to construct a confidence interval, and even if my p-hat value fell right at the edge of this interval, I'm trying to construct a confidence interval that's big enough that it will still capture, if you think about it like this, if we carry this blue value down, it still just barely captures the true value of p. And so basically the width that I need to make my confidence interval is this distance. Well, it's technically double this distance. This is my margin of error. And so that's the value m I'm looking for. If I can figure out what this z-score is, I know the z-score at the center is 0, and I can figure out the length of m in terms of a z-score. And then we'll just use the standard error from part C to convert from z-score to back to the units of proportion that we're trying to actually deal with. So that's the idea. I need to figure out in this step this z-score at this boundary. So 96% of the area is on the inside. If this was an easy problem, I would have given you a number like 95%, and we would have gone. So the first thing we should do to figure out the critical value, z sub alpha over 2, to figure out what it is the first thing we should do is go over here to table A3 and look and see if that 96% confidence level shows up. And sure enough, it does not show up. So 95 shows up, 98, but there's no 96. We can still use this, and in fact, we can use this as kind of a sanity check. 96 would sit somewhere right here, right? If 96% was on here, it'd sit right here, and it'd be kind of in between this value and this value. So even though it didn't show up, the critical value associated with 95% is 1.96. The critical value associated with 98% is 2.326. And the one for 96% must be in between those two numbers. So we're going to find it in a minute, but just know ahead of time, it better fall between these two numbers. If it doesn't, it just doesn't make sense. We made a mistake if it doesn't fall between 1.96 and 2.326. And it looks like because 96 is a little bit closer to 95 than to 98, I'd actually expect it to be a little bit closer to the 1.96 than the 2.326. But we'll see how that goes. Okay, so we don't know it exactly, but we kind of have a ballpark for it. How can we find it exactly? Well, here's where the stuff we did in chapter 7 comes up. We need to actually basically do kind of a search, a reverse search to find the z-score associated with a certain area. If 96% of the area is in the middle, then that means over here and over here, the remaining amount of area is 0.04. But that 0.04 is, again, split 50-50 between the two sides. So how much is just on the left here? 0.02. And so I'm going to fill that area in red as well. We have 0.02 right there. And if I want this z-score, I need to do basically a reverse lookup in our table and find the combined area that goes from there all the way over to the z-score of interest. So including the tail. I know it's the 96% in the middle plus the 2% in the left tail for a total of 0.98. I need to go look in table A2, which I'm allowed to do because we're dealing with a normal distribution, right? Because it's a population proportion, I know we're dealing with a normal distribution. So I can go to table A2 and I need to find the z-score associated with an area of 0.98. So here's table A2, and again, you'll have this table provided for you on the exam. But go to the table, and I'm looking for the area 0.98, or a number as close to it as possible. So all the areas, again, are in here in the middle, and the z-scores are on the edge. So 0.93, 0.96, 0.97, 0.9, 0.98. So we've gone past it here. So it's somewhere in between these. Let's just go through this row. And it looks like, here we go. Here's two numbers that are close. This number is a little bit smaller. This number is a little bit bigger. And so we just need to pick whichever one is closer to 0.98. So looking at the two of them, this one's off by 0.0003. It's 0.003 more than 0.98. And this one's off by 0.0002. It's 0.0002 less than 0.98. So this one's actually a little bit closer, and it's the one I will use to pick my z-score. So let's find the corresponding z-score. We go back out this way, we go back out this way, and the corresponding z-score is going to be 2.05. And so that is the value that we should use for our critical value. This value right here is 2.05 according to our table, 2.05. We could also do that over here if you wanted. So we could turn on the calculator and we could do a normal distribution. So go into our list of distributions and do the inverse normal. So we could also do it that way. It'll ask for the area. We'll have to enter that 0.98 that we just found. It'll ask for mu and sigma. We want to do it. We're looking for a z-score. So we're looking for a standard normal distribution where the center is 0 and the standard deviation is 1. So we'll leave those as 0 and 1. And it should give us a z-score very close to the one that we just found. We'll paste it, hit enter. And sure enough, it's 2.0537, yada, yada, yada. So 2.05 is correct, at least rounded to 2 decimal places. Okay, so that was the hard way. Again, if this number had just been 95 or 98, it would have been a 2-second lookup over here. So that should always be your first stop, is go check and see if the confidence level prescribed shows up in this list. And we can double check our 2.05. Is it indeed between these two numbers where we suspected it would fall? And sure enough, it is. And even as I said, it looks like it's a little bit closer to the 1.96 than the 2.32. If you were to actually look at the difference between this number and each of those numbers, it's a little closer to this one. Okay, so we've got our critical value. Should have been 2 seconds, but instead we had a crappy percentage that wasn't in that table, and so we had to do that extra work. But this is in general how you do it. You figure out if you've got 96% in the middle, that leaves you 4% left over, half on each side, so 0.02 plus the 0.96 gave us the 0.98 that we wound up using. So the next step is to compute the standard error. The formula for the standard error is basically related to, for these population proportion problems, it's related, you'll recall, to the binomial distribution. So it should look kind of familiar. It looks like the square root of p hat times 1 minus p hat, whole thing divided by n. So that's the formula for it. Probably something you should just have written down on your note card. And we'll plug in the numbers. So this is going to be the square root of p hat that we found. That's our point estimate from the first part. It's 0.718. So 0.718 times 1 minus 0.718. And then I divide the whole thing by the sample size, which was, for us, 78 voters. And so I can plug that into the calculator. I'm going to do a big square root of 0.718 parentheses times 1 minus 0.718, close my parentheses, divided by 78. Hit enter, and it looks like this number is about 0.051-ish if I rounded that to 3 decimal places. And so we've got what we need now to compute our margin of error. We figured out that this distance that I've drawn in here in blue for our margin of error, in terms of z-scores, that distance is 2.05 z-scores. But I don't want it in terms of z-scores because we're asking about a proportion. I want to convert that to proportion. For us, one standard deviation is 0.05 in terms of proportion. And so 2.05 standard deviations means I just need to take this number and multiply by 2.05 to get the actual margin of error. So our margin of error is, the formula for it is going to be, we'll take our z sub alpha over 2 times the square root of our p hat times 1 minus p hat divided by n. Basically, we're multiplying step 2 and step 3. We're going to get 2.05 times 0.051, and that gives me 2.05 times 0.051, 0.10, let's round that to 0.105. And so the last step is to actually construct the confidence interval. We figured out that this distance now, in terms of proportion, is about 10%, 10.5%, 0.105. So that's the amount of buffer that we need to build on either side of our point estimate. If our point estimate fell right here, if this is where 0.718 is, I need 0.105 to the left and 0.105 to the right of that number. So this one, again, the way that you would do this, the confidence interval is going to be p hat plus or minus our margin of error. And again, I would encourage you to write these formulas as I'm doing here, or at least like the symbols, so I can give you some partial credit in case you screw up these numbers. But what we're going to get out of this is, for the lower bound, I'm going to do the 0.718 minus 0.105. And that'll give me 0.613 for the lower bound. And then I need to do the same thing. I can go up and highlight it, hit enter, and let me just change that minus sign to a plus sign and hit enter. So now I'm adding 0.105 to it for the upper bound to be 0.823. And so in this case, it is between, let's see here. So the percentage of registered voters that voted in the last election, we think we're 96% confident that it's between about 61.3% and 82.3% of registered voters voted in the last election based on our sample that we took. So if we had to write this as a sentence, that's how we'd write. We are 96% confident that between 61.3% and 82.3%, just converting these decimals to percentages, of registered voters voted in the last election. And then I'll check those comments in a minute. I see I missed quite a few. Let me check it out here. Sorry, I didn't have the chat open, so I saw that there's some stuff in the chat. And of course, I missed those questions. And we're going to do this on the calculator in just a minute. Okay, I totally missed when clearly these are old questions. So if you don't mind, at the end, maybe we can come back to them. You can pipe up and take me back to wherever you had this question if I haven't answered it between now and then. So sorry I missed your question, Jake and Cindy. But for Danielle, let's do this whole thing on the calculator right now, if that's what you're asking. Okay, so I kind of did it step by step. This is the way you would do it on any calculator, assuming you just had the tables, you didn't have a fancy TI graphing calculator. But if you've got the graphing calculator, we can jump straight to this answer really easily. However, I'm still going to make you give me all this information along the way, so you kind of need to know how to do it this way regardless. So let's do this on the graphing calculator. If I was doing this problem on the graphing calculator, the first thing we want to do is hit our stat button. And so remember, this might be worth even putting on your note card. Like if you want to, try to make this tiny and put it on there. But I even gave the calculator command. So for population proportion confidence interval, the command is 1propzint. So all I need to do is go to my tests. So go over to my tests and look for a 1propz interval. And it's down a bit. There we go. Z interval, T interval. 1propzint, option A. And it asks for, in this case, X, which was 56, out of N, which was 78, and the confidence level is 0.96. And I think you can just write 96 as well. I don't think you need the decimal. So that's how we enter that, hit calculate, and it literally spits out the two numbers that we did all that work for us. So it gives us 0.61331. So a few more decimals of accuracy than we did here. And similarly, 0.82259, a few more decimals of accuracy than what we have here. It will also give us p hat, our population, our point estimate that was the population proportion up here, the 0.718, it spits that out for us. But to get these intermittent values, you're going to have to go back and use the table anyways. So just know on the real exam, if you have a graphing calculator, my recommendation would be use it first, get the final answer, but you're still going to have to go back and fill in your work, and hopefully you can kind of double check your answer here by actually doing the work along the way. Similarly, just as a general tip on your note cards, which again, you'll be allowed to use the same note cards as before, 3x5, double-sided. If you want to try to like write a compact way to memorize how to do all these confidence interval problems, really it's a 5-step process that we've written down. So if we just write all those steps down, the first step is to find the point estimate. And in fact, let me delete this and I will clean this up even more compactly. You can almost make like a little table and think about wanting to do the point estimate and all these various other things for a couple of different categories. So basically, if you wanted to do an 8.1 type problem versus an 8.2 problem versus 8.3. So imagine that you've, well, let me give myself a little more room than that. Might need a little bit more. Depends on how tiny I can write here. So 8.2, 8.3, because really they all involve the same 5-step process and there's just little tweaks. So the point estimate in 8.1 and 8.2, we're trying to find the mean. We're trying to make a prediction about the mean, and the point estimate is going to be X bar. It's going to be our sample mean. Whereas we just saw in 8.3, it's p hat, which was X out of n, the number out of the total sample size that met whatever criteria we're looking for. Step number 2 is always finding the critical value. For 8.1, that's a z-score. It's z sub alpha over 2. Similarly, for 8.3, what we just did, it was a z-score. But in 8.2, it's a t-score, and we're using a t distribution, so it's t sub alpha over 2. For step number 3, that's where we want to find our standard error. And again, this is the main formula that changes. In 8.1, it's sigma over the square root of n. In 8.2, it's s over the square root of n. And in 8.3, it's that formula that we just did right here. So the square root of p hat times 1 minus p hat divided by n. All of that in a square root. And for step number 4, we find the margin of error. And in step number 5, we actually find the full confidence interval. And these are simple in the sense that, maybe I can erase this because it's the same step for all 3 cases. Step number 4 is just basically take step 2, that result, and multiply it by the result of step 3 to get step 4. So you always take the critical value times the standard error. So it's this times this in case of 8.1, or this times this in the case of 8.2, or this times this in the case of 8.3. And then finally, for to construct the full confidence interval, it's always going to be take the result from step 1 and both add and subtract the result that you just found in step 4. We add and subtract our margin of error from the point estimate. And so this is basically a compact way, if you can get your handwriting tinier than what I've got here, that you can fit this in one tiny corner of the note card and basically have the steps written out for how to do all 3 different types of confidence intervals. So again, these are all for the different confidence intervals. So just a thought, while I'm talking about the note card, let me just mention this. I had sent out that announcement that said there would be an extra credit problem on this exam 3. There is going to be. It's going to be a problem similar to stuff from exam 2. So it's going to cover material from exam 2 because exam 2 did not go super great. Wasn't terrible, but it wasn't as good as I'd hoped. So I think one of my problems was just worded in a way that people didn't quite understand what I was asking. So I'm hoping that this will give people an opportunity to kind of make up some of those points. So just keep in mind, there will be one problem from exam 2. It won't be verbatim from exam 2, but it'll cover the same concepts. So you're welcome on this exam, if you'd like, to basically have 2 note cards. Have your old note card from exam 2, if you've still got that lying around. That can help you with the extra credit problem, and then just make a new note card for exam 3 for the rest of the exam. So instead of having to make like a special custom note card that has tried to fit both exam 2 and 3 onto, just feel free to use your old exam 2 note card plus a new one for exam 3. So keep that in mind. I'll try to send out an announcement about that. And specifically, it's going to be material from chapter 6. I'll narrow it down. It won't be chapter 4 or 5 stuff. It'll be from chapter 6. That's what your extra credit problem will be. So if you want to go back and try to study that to help boost your grade, that's all I'm going to tell you. Okay. Any questions about this? Hopefully this is kind of maybe a helpful thought of how to organize things on your note card. Okay, then let's move on to problem number 12 here. Okay, it says the heights of American women follow a normal distribution with a mean of 65 inches and a standard deviation of 3 inches. In part A, we want to know what is the z-score of a woman who is 68 inches tall. In part B, we want to know what's the z-score of a woman who's 59 inches tall. In parts C and D, we want to respectively compute the probability that a woman falls between 59 and 68 inches, so falls between these 2 z-scores. And then down here, we want to draw the picture. So here's our keyword right here in part C. What is the probability, ... There's our indication. What is the probability of that we're dealing with a chapter 7 problem? So the next question is basically, are we dealing with a single individual or sample mean? When we compute this probability, are they asking about the probability that the sample mean is between 2 values or that a single person's height is between those 2 values? And so in this case, we want to know what is the probability that a single randomly chosen woman has a height between 59 and 68 inches. So this is like from 7.1, 7.2. We don't have to do anything tricky. There's no standard error that we need to use. We get to use just straight up mu and sigma. We don't have to use sigma divided by the square root of n or anything like that for our standard deviation. So just keep that in mind. It's one of these types of problems. Okay, so let's come back down here and let's find these 2 z-scores. So just notationally to make it a little easier, so it's easier to see what we're talking about, I'm going to make it kind of like function notation where you do like f of x, if you've ever seen this. And it just means you get to input different values. That's kind of what I'm thinking of. Z is kind of a function that spits out a z-score. Just for this, the only reason I'm doing this is because we have to do 2 of them. And I want this one to be distinguished from the one on top. So think of it kind of like that. But you could use other notation, doesn't really matter. You don't have to do this at all. You could just call it Z. But the general idea is we take the value of interest, we subtract off the mean, and we divide by the standard deviation. And again, I'm able to use just sigma for the standard deviation and not sigma over the square root of n, because we're only going to be interested in a single randomly chosen person's height, right? It's the z-score of a single woman, not of like a mean average or anything tricky like that. So in this case, we take the value of interest, which is 68. We subtract off the mean, which is given in the problem up here, which is 65, and divide by the standard deviation, which is 3. We don't even need a calculator for this, hopefully. 68 minus 65 is 3. We get 3 divided by 3, which is 1. On the real exam, I probably won't be so nice. I'll probably give a number that you have to actually plug into a calculator, and you'll get a decimal answer instead of a whole number. But either way, it doesn't make conceptually much difference here. Do the same thing here. 59 minus 65 over 3. Well, 59 minus 65 is -6. divide that by 3, and we get -2. So there are the two z-scores. And again, if you can't do this arithmetic in your head, that's not a big deal. Just do it on the calculator. I'm just not going to display that here, but hopefully that's okay. Okay, so here's the two z-scores. Maybe before we do this, I often find it helpful to draw the picture first. So I'm going to start with the picture and then compute the probability. But basically, I have to label this graph appropriately. So I also need to locate all the different points that we're interested in. So essentially, I'm interested in all the different z-scores. We can label this a couple of different ways. We could label it in terms of the random variable x, which equals like heights, or we could label it in terms of the z-scores, which are, again, z-scores. The average height was given to be 65, so I know that's the center in inches. The height in inches is 65. If we instead labeled it in terms of z-score, that's just a z-score of 0. The next height we were interested in was 68 inches, which was 1 standard deviation. That's going to fall right about, if I had to ballpark it, right about there-ish. So in inches, that was 68 inches. It is a z-score of 1. And so I'm doing both, just to make it totally clear. I'm labeling it both. Here's all the x values. Here's all the corresponding z-scores. You don't have to do both if you were to do this. You could just pick one or the other, and I don't really care which. So just keep that in mind. The last one we need to enter is 59 inches, so below average, and we said it was 2 standard deviations below. So here's 59 inches. And really, you can see that we're counting by threes, right? This distance, I'll do it real quickly and then we'll erase it, right? It told us the standard deviation is 3 inches. So essentially, we're just counting by threes as kind of we go in either direction. So that means that this number right here, for example, would be like 62. And if we went out another standard deviation on this side, we'd be up to what, 71. So we're just kind of counting by threes if you think about it that way. And we're interested in finding the probability that somebody was between 59 and 68, which if I draw the z-scores, let me remind you, the z-score corresponding to 59 was -2. So I'm interested in this area right here. That is the area that we're trying to compute. So again, there's a couple of different ways we can do this. We'll do it on the table, but we could also do it on the calculator. And I know there's 1 or 2 people that are also using Excel. Maybe I can pop that up and do this on Excel real quickly as well, just as a reminder for a practice. Anytime you have to find the area under a normal distribution, you can do it any of those methods: calculator, table A2 or A3, in this case A2, and or Excel. Okay, so what is this probability? What is this area? If I want the probability that basically the x value is between 59, so 59 is less than x is less than 68, we just saw that that's the same as saying the probability that the z-score is between -2 and +1. And the way that we had to do these was basically take the area associated with the z-score of 1, which would be this whole shaded area plus this little tail, and then subtract off just the little tail, which is the area associated with the z-score of -2. So we basically split it. If we're using the tables, we split it into 2 separate pieces. We do the probability that z is less than 1, and from that we subtract the probability that z is less than -2. So that's how we would do it on the table, right? Basically take the big area, we do it in 2 areas. We'd take the whole combined black and red area, which is the area associated with the z-score of 1, and then we'd subtract off the little red area, which is the area associated with the z-score of -2. And that's exactly what we're doing right here. So if we were using the table, I just need to go look those z-scores up. Z is equal to 1, and again, we're dealing with the normal distribution. So here is z equals 1, 1.00. We're looking at this number right here, 0.8413. So let me write that down. So this first number is 0.8413. And then we need to look up the z-score for -2, which is Here's the negative z-scores, negative 2.0. So first column, negative 2.0.0228. So let's go back, 0.0228. This is what we're subtracting off, 0.0228. And when we do that subtraction over here, 0.8413 minus 0.0228, hit enter, we get 0.8185-ish. So there's our answer. We could have also done the whole thing on the calculator, so let's do that. Instead of using the table, how would we do this one? So we would need to use the normal distribution. So again, hit second vars to get to our list of distributions, and we're going to use Normalcdf. Hit enter. It will ask for the lower and upper. And again, my calculator is newer. I know some of you have calculators where it doesn't take you to this menu, but the idea is in general, it will be, let's write it here, normal CDF, and then we have to enter 4 pieces of information: the lower bound, upper bound, mu, and sigma, in that order. So for us, the lower bound, we could do it either in terms of z-score or in terms of just the original inches. So if we're doing it in terms of inches, the lower height I was interested in was 59 inches up to an upper bound of 68 inches, where the average height was 65 inches and the standard deviation was 3 inches. We could have also done the exact same thing with the z-scores. If we'd already computed those z-scores, we could go from a z-score of -2 up to a z-score of +1 on a standard normal distribution where the average value is 0 and a standard deviation is 1. These two commands here, entering those two different sets of numbers, will give us the exact same answer in both cases, and it should be very, very close to this one. So in this case, let's do the 59 inches up to 68 inches, a mean of 65, and a sigma value of 3 inches, and hit paste. So again, here's what yours would look like. If you don't have that menu, if it just does Normalcdf, then you have to type stuff. Here's what you would type: 59, 68, 65, 3, exactly as is written there. Hit enter, and there we go. 0.818594678 So in this case, if we were to round to 4 decimals, we'd actually get a 6 there. This was the issue people ran into on the homework when it wanted you to use the calculator, but you use the tables. Sometimes you'd be off in like the last decimal. In this case, I'm not going to care. Whether you choose to use a table or a calculator, it's up to you to get that answer. So there's the answer that way. Again, my argument was you could use this same thing and instead enter whatever I just said: -2, 1, 0, 1, and close my parentheses and then delete the rest. So I could enter this set of numbers, all the z-scores instead. And sure enough, you can see to all decimals, it matches exactly the answer that we got above. One last real quick thing. Let's do this in Excel. I think you can see this. Let me just make sure. If you cannot see my Excel, it's giving me a warning that for some reason you wouldn't be able to see it, but I think I'm sharing it. I think somebody mind in the chat, can you guys see the Excel page over here?
No.
No, you cannot see it? Huh.
No, we cannot see it.
Okay. Thank you. Let's try this share again and see. Have you guys been able to see my calculator this whole time?
No,
God, why didn't you guys say something?
because we thought you were just doing it on your own, but someone put it in the chat. Can you show your screen for the calculator about 30 minutes ago?
I see. Okay, I thought you were just meant for me to do it that time. Okay, I'm so sorry. I thought I was sharing the whole thing with you. And I've been clicking over here thinking I was showing you every little step, and sure enough, I was only sharing my whiteboard and not my whole screen. Okay, I apologize. Real quickly, let's go back and just for the sake of everybody watching this, let me go redo everywhere that we've done something on the calculator. At least on these word problems, let's do it on the calculator here. Okay. So let me come back to this problem and do it on the calculator. Then I'll redo what we just did here on the calculator as well. Well, I'm sorry. I thought you guys could see that the whole time. So now I feel like an idiot. Okay. So this command here, to get the confidence interval for this problem, we're going to hit second vars to get to our, I'm sorry, no, this is the, I'm on the wrong problem. We're going to hit the stat button and go to our tests because we're doing a hypothesis test. So here is our, I hit the stat button. Here's, I scrolled over to tests. Here's our long list. We just need to scroll down till we find that one prop Z test. And it's down a little further. Oh, sorry, one prop Z int. We're doing a confidence interval. Now I'm all flustered. Okay, just totally clear. This is the command that we're using. That is the command that I've now found over here by hitting stat, going to tests, and then scrolling down to one prop Z int, one prop Z int. So there's what we need. Here are the numbers as I entered them before, the 56, the 78, and a confidence level of 0.96 that matched the 56, 78, and the 96% that we had there. And I hit calculate. And now you can see that the numbers that we got right here match the numbers I've got right here, but with more decimals. Okay. I'm so sorry, Danielle. I totally misunderstood the question you were asking. I thought you were just asking me to do the problem on the calculator, but now I understand. I will assume that you know how to do, were there any of these that were tricky that we needed to do on the calculator? I don't think so. I think they were all just dividing and fractions. So I'm assuming you can do that stuff. Similarly, I think I entered this into the calculator. And I, like, for example, to do this part right here, if I wanted to compute this 0.051 that we found for the standard error, I can show you how to do that real quick. So I just hit the square root, 0.718. You can literally just type in parentheses to do your multiplications. Do 1 minus 0.718, close my parentheses, and divide by 78. So basically it's typed on my screen the exact way that I have it written here. And I hit enter, and there's where I got the 0.051. So 0.0509. I rounded that up to 0.051. Any other questions about anything I've done on the calculator? Was there anything else that I should go back and do that I'm spacing out? Okay. Then let's do this one real quickly. I'll just assume that you know that I can do it both ways, but so to do normal CDF, that is a distribution. Here we're just dealing with the distribution. So now I hit second vars to go to my list of distributions. It's the second option, normal CDF. And here's where I put my lower bound, my upper bound, my mean, and my standard deviation. So these 4 numbers. And again, if you have an older one, it may not give you this menu screen. It may literally just print out normal CDF with the parentheses and wait for you to manually type in this list of numbers with commas in between. So it may give you something that just looks like this. Normal CDF with all those numbers. Okay, and I hit enter, and there is that number that I wrote down right there. Okay, hopefully this all makes more sense now, and you have some idea of what I'm actually doing over here. Now, can you see my Excel page?
Yes, we can.
Okay. Make sure that it's not app specific what I'm using over here. Okay, so if I wanted to get the same number here in Excel, the same idea, I would have to kind of break it down. If we start typing, so we do an equal sign to start our formula and just start typing norm. And the first thing that pops up is norm.dist, and that's what we need. And it'll ask for the X, mean, standard deviation, and cumulative. It doesn't let us do a lower bound and an upper bound. We're going to have to basically do these 2 pieces separately. So it's not really that much easier than just using the table. So in this case, but we could potentially have used just, I will mention, we don't have to use the z-scores. I could use like the 68 inches. So 68 inches, that was from a distribution where the mean was 65, the standard deviation was 3, and we'll always do true on the normal distribution ones. So hit that, and sure enough, we get 0.841345. We basically get that number. Then I'll have to do the same thing. So equals norm.dist. And we'll now do it for the lower bound. 59 inches with a mean of 65, a standard deviation 3, and true. We do want it cumulative. And that gives us 0.02275. So very close to the same number that we got here. And now I can just do equals, click on the first number, do a minus symbol, click on the second number, and hit enter, and it will subtract those two numbers for me. And there is this number, but again, with more decimals. Okay, so that's how you can do that in Excel. So pick your poison, table, calculator, or Excel. And hopefully the spreadsheet works a little bit better this time. I did check normal distributions worked in Excel the last time I did it, so I'm hoping that they do in there. I know the Respondus Monitor spreadsheet is kind of funky. Okay, final problem. Let's bring the calculator back up for now. Let me put this back in, my apologies, let me put this back in writing mode here. Okay. The mean weight of an American male is 190 pounds with a standard deviation of 27 pounds. A sample of 38 males from New Mexico is found to have an average weight of 182 pounds. Can we conclude that the average weight of a New Mexican male differs from the national average? Use a significance level of alpha equals 0.05 and the p-value method to determine your answer. I will just mention, I know we've done both the critical value and the p-value methods. On the exam, I'm just going to make you do the p-value method. It's by far the more common method in real life, and it's the more useful method. It gives us more information. The p-value itself is an interesting number, and I'll address that when we get there. But just know you're going to have it. It's going to be a p-value problem as opposed to a critical value problem. Okay, so the first question is basically kind of similar to what we had before. We can kind of, by process of elimination, narrow down the type of problem we've already had. Here was our chapter 7 problem, and I should have mentioned this is basically like a 7.1 or 7.2 type problem. We've had our chapter 8 problem, so it pretty much guarantees us that that last problem is going to be a chapter 9 problem, but let's just go check. All right, let's look at our decision tree. What I'm looking for are the words significance level, and we know right now it's going to be for the mean, so we've just got to decide whether we are dealing with sigma or S, and this is, again, just going to be reading comprehension to determine that. So let's make sure the word significance level shows up in this problem. And sure enough, there's our significance level. There's our keyword. We know it's a hypothesis test. And now we just need to decide, is this a 9.2 problem or a 9.3? And that's essentially what we're determining here in part A. It gives us a standard deviation of 27 pounds. Is this sigma or is this S? So they give us a standard deviation, and it's up to us to decide, is this the standard deviation of the sample of 38 males or of all American males? So what's the answer? Well, based on the wording, it tells us the mean weight of essentially all American males is 190 pounds, and the standard deviation of all American males' weights is 27 pounds. So this 27 pounds is indeed sigma. So we're given sigma, not S. It would have to be phrased where it didn't give us this. So if it just ended that first sentence there, and then move that sentence down into the second sentence instead. A sample of 38 males from New Mexico is found to have an average weight of 182 pounds with a standard deviation of 27 pounds. That would change it and make it so that the 27 pounds was referring to S, because it would be in the second sentence, modifying the sample of 38 males from New Mexico. It would be referring to that group instead, to our sample. Is that clear though? It's literally reading comprehension. There's no magic like keyword you can look for. There's nothing special. You just have to read it very carefully. They'll tell you a standard deviation, and it's up to you to determine when they mention that standard deviation, are they talking about the full population of everybody or just the sample that was taken? And so for us, it's sigma. Because it's sigma, that means that we're dealing with a normal distribution. If it was S, we would be dealing with a t distribution. So sigma always goes with normal, S always goes with t distribution. Okay, so we've narrowed it down with that in mind to section, what? That's 9.2. Let's just go verify. Right, it's with sigma known, so that's section 9.2. We're dealing with a normal distribution, so dealing with z's. This is going to be a z-test problem when we get around to doing it. Okay, so this is 9.2. Okay, so now we need to state our null and alternate hypothesis. So this is the equivalent of our normal step 1 in the 6-step process that I have outlined in the videos that I created. So H0 and H1. Here's our two hypotheses, and we'll use them to decide whether it's left-tailed, right-tailed, or two-tailed. So I know right off the bat, because we're trying to find the mean, I'm gonna have mu equals and mu here. This much I can do without doing anything. I know the null hypothesis always has an equal sign. We're dealing with an average, so I've got mu here. So we're good to go. We just need to figure out what number goes here. Whatever number goes here also has to go here. They always have to be the same number, and then we'll have to figure out what symbol goes here. And that's gonna also be, again, based on the question and evidence that's given. So in this case, the question that's being asked is, can we conclude that the average weight of a New Mexican male differs from the national average? It's not asking if it's less than, it's not asking if it's greater than, it's asking if it differs. And that tells me that word differs is the key. This is going to be a two-tailed hypothesis. This is going to be a not equal sign. The evidence suggests, let me just erase all of this so we can read everything. The evidence suggests that the average weight in our sample, 182 pounds, was less than the 190. But it didn't ask us, can we conclude that the average weight of a New Mexican male is less than the national average? We just said, does it differ? And so that's why we use a not equal sign and not a less than symbol. So again, another thing that people often mess up on. So it's that keyword differs. Oops, differs. That made it be a not equal sign instead of asking, can we conclude that the average weight of a New Mexican male is less than the national average, in which case it would be a less than symbol. But that means this number needs to be 190. If the answer to this question that was asked is no, right? So if the average weight of a New Mexican male doesn't differ from the national average, if the answer is no, that corresponds to the null hypothesis, and the average weight of a New Mexican male would in fact be equal to 190. So this is basically if the answer is no, right? The null hypothesis being true. So the null hypothesis always essentially corresponds to answering the question that's asked here with like in the negative, answering it no. But this always has to be the same number. So these have to always be the same number. So keep that in mind as well. But this thing is two-tailed. Any questions from anybody about this? Honestly, this is the thing that people seem to screw up on the most if you screw up the null and alternate hypothesis. Any questions about this at all? Not even this one specifically, but just more general even. Then I guess the one other thing that I want to mention is just notation. And again, I stress this to some degree in the video, but this is not, you can't do this. This is an incorrect answer. H0 and H1 are just labels. This is basically like we just, instead of writing out the word null hypothesis, we didn't want to have to write that long word out every time. So we just gave it a symbol, H sub 0. And instead of writing out the words alternate hypothesis, we just called it H1. So this needs to be a colon. This needs to be a complete mathematical statement. Mu equals some number. So the average weight is equal to 190 versus the average weight is not equal to 190. So just keep that in mind. This notation is bad notation. And I will mark off points for this. It's mu that's equal to 190 or not equal to 190, not H0 and H1. So just keep that in mind. Okay, so this was our step 1. Step 2, we need to give the significance level alpha. This corresponds to our normal step 2, where basically what we're trying to do is define what we're going to consider weird. And that's exactly what alpha tells us. When it asks what does this number represent, it's basically the probability that we're going to consider weird. And according to the phrasing up here, we're supposed to use alpha equals 0.05. So our significance level is alpha equals 0.05. This is the probability that we consider weird? How unlikely something has to be before we say, hey, that was weird that that happened? Okay. Down here, and of course I managed to screw up. These labels are wrong. I put the wrong one in here. These should be all the possible values of x bar, and this should be mu at the center. We'll try to make sure that I don't have any of these silly typos on the real exam. Okay. So in this case, we're asked to basically indicate the region represented by the significance level in this figure. Well, in this case, it's two-tailed, and that means that this area, so probabilities, you'll remember, are also always the same as areas, so probability slash area, that we're going to consider weird. And in this case, because it's two-tailed, I have to take this area, which is tiny. It's only 5% of the area, right? Remember, the total area under the curve is 1. This is only 0.05. I have to now split up that 5% of the area 50-50 between the two tails. If this had been a normal, just a right-tailed hypothesis or just a left-tailed hypothesis, I wouldn't need to do this. We wouldn't have to split up alpha. So the notation in this case is basically I need alpha over 2 on each side. So I'm going to take alpha, which is 0.05, and I have to split it 50-50 between the two sides. So let's chop it off here and here. Let's say those are the regions, meaning over here I have 0.025. There's half of alpha. And the other half of alpha wound up on this side. So here's the other 0.025. And this 0.025, I'm literally getting it by taking this number and dividing by 2. So this is literally alpha over 2. So these are the regions that I'm going to consider weird. As if you want to think about it, we can almost put like a dividing line here. This is the not weird region in the middle. These are where if results fall in here, they're close to the average value that we expected to see. But if they fall out in these tails, that's where we consider our result weird. They're very far from the average we were expecting. So here's our picture. We'll come back to this picture in a minute. Part D says to compute the test statistic. This is equivalent to our normal step 3 in our process. So in this case, the test statistic is a z-score. Remember, we've now got our setup where we've defined what's weird. We have a value of our x bar value is 182. Right? So right now we know that basically we're assuming that this value in the middle, this mu, is 190. We're assuming the null hypothesis is true, that the average weight of the New Mexican males is equal to 190 pounds. And we're going to see, where does the evidence fall on this picture? Does it fall into a weird region or a not weird region under that assumption? And our evidence is that the average New Mexico male in the 38 males that we sampled was 182 pounds. So I don't know exactly where that is, but I know it's below average. So it's going to be somewhere over here on the left. So this is the question. We found x bar equals 182. And the question is, where does that 182 fall? Does it fall over here? Does it fall over here? We don't know where it's going to fall. If it falls way over here, that's a weird result. It means it's really unlikely that we got a sample of 182 just totally by chance if the true average should have actually been 190. But if it falls over here, we'll say, well, that's definitely still below average, but it's not so far from what we expected that we consider it a weird result. And that's really what this boils down to. We're trying to decide exactly where our evidence, so this is our evidence, that x bar equals 182. We're just trying to figure out where it falls. Does it fall in a region that would be really weird for that to happen, assuming that mu was equal to 190? Or does it fall in a region where that's not that weird of a result to see happen if mu equals 190? And we've arbitrarily decided at the beginning, based on what alpha was prescribed to be, that's how we decided what we're going to consider weird. Alpha is what determines weird, how we define weird. Okay, so now we need to actually find the z-score so we can try to get a sense of where 182 actually falls. So let's find this z-score. The formula for the test statistic in this case is we take our x bar value, we subtract off the mean, so mu 0, which is this value right here, 190, And then we divide by the standard error, which is sigma over the square root of n. And this pattern holds whether you're doing section 9.2 or 9.3. It's going to be, in this case, it's x bar minus mu naught over sigma over the square root of n. If it was 9.3 and we were dealing with a t-score instead, we'd replace the z with a t. And the only other change is we'd replace sigma with s. So if it was 9.3, just those two letters would change, but the formula would otherwise be untouched. So I would put those two formulas in your notes for these two different test statistics. So we just need to plug in those numbers. We got 182 minus 190, and then we're dividing by sigma over the square root of n. I think it was 27 pounds was the standard deviation. Let me go see. Yeah, 27 pounds, and our sample size was 38. So this is 27 over the square root of 38. And let me just toss some parentheses around this, and we can kind of enter it into our calculator that same way. So again, I'm going to do parentheses 182 minus 190, close those parentheses, do my division, and now do the denominator, parentheses 27 divided by the square root of 38. And click the arrow to get out of that square root and close the parentheses and hit enter. And we get, this is about negative 1.83 if I had to round it to 2 decimals. Good enough. So there's my test statistic. And that's going to be hard to tell. So we're almost 2 standard deviations below average, right? Negative 1.83, 1.8 standard deviations. If I had to eyeball it, ooh, it's close. Like this is close to where I would think 2 standard deviations would be really close to this number right here. So I don't know if we're going to be just a little to one side or the other. My guess is if this is 2 standard deviations, I'm guessing we're going to fall here, but we can't tell that yet. I have 1 z-score, but I don't actually know the z-score of this cutoff for what we considered weird. If we were doing the critical value method, that's what I would be comparing. I would know the z-score. We would have found it back here in this step. We would have had to find the z-score associated with this cutoff between the not weird region and the weird region. I'd know this z-score. And I'd immediately be able to compare it to this z-score to know whether this z-score falls to the left or the right of this z-score. But that's the critical value method. The critical value method allows us to determine whether our result is weird or not, basically if it falls here or here, by comparing 2 z-scores. The p-value method does the same thing. It allows us to determine if our answer falls here or here, but in this case by comparing 2 areas instead of 2 z-scores. So let's find the area, and that's what the p-value does. So this is step 4 in our normal process, where we compute the p-value. The p-value is basically the area to the extreme of the test statistic. So once we found this test statistic, we're going to find the area associated with that. It's also equal to essentially the probability of getting the result that we got. So it's the probability of getting our evidence by chance. So conceptually, those two things, I'll come back to them in a minute once we have the actual value. So let's find this area. We have a couple of different ways to do it. One is on the tables. I can use this z-score to find the area to the left of it. And then we'll have to double that number only in this one case because it's a two-tailed hypothesis. Right? I ultimately want to compare the p-value to alpha. Right now, alpha is spread 50-50 between the 2 sides. So it's not fair to compare only one side of area to alpha where alpha is spread across both sides. So we're going to have to basically find the area on one side for our p-value and then double it to get the real p-value that we can compare to alpha. So let's do that. I want to find this area associated with z equals negative 1.83. Let me go find those tables. They're up here a ways. Okay. So find the negative z-scores. It was negative 1.83. Let me zoom in so we can all read it. Here is the table I need. Here's negative 1.8. Here's 0.03. Those two things meet right there. So there's the number, 0.0336. But again, That's just the area to the left of that one given z-score of the z equals negative 1.83. So I know, here's the picture, here we go. What we basically just found, let me erase this part because we're about to identify where it goes. It turns out that it is going to be over here, that this is going to be the cutoff, because I just found that this area was 0.0336. So it turns out this must be where our 182 is. But that's not the total p-value, right? I'm trying to find this area. It's 0.0336, but it's not fair to compare that red area to alpha, which again is split between both sides. So I need to double this number to get the combined area, because I also want the mirror image of it over here. Get another 0.0336 on this side, and that combined value between those two values, they make up the p-value. So that combined area is going to be the 0.0336 times 2. So I'll do 0.0336 times 2. And so that's going to actually be the p-value. It's, oops, wrong color, 0.0672. So that's the p-value that I found, 0.0672. So essentially what you can see is, because we found a larger area than 0.05, we're winding up with our cutoff where our evidence fell right here, not falling into the weird region. If we'd instead gotten an area that was less than 0.5, well, that would have had to have been bounded by a tinier region that was further into the tail on both sides. And we would have been assured that this X bar would have had to fall somewhere over here further to the left to get a smaller area than the 0.025 that we're getting over here. So that's kind of the idea. So this is the p-value that we just found. It is also, as I said, the probability of getting our evidence by chance. So if we go back to the original question, we said we're going to consider something weird if it would happen by chance less than 5% of the time. So if something has less than a 5% probability of happening, we're going to, and it happens, that's considered a weird result. Well, it turns out the result that we got, X bar equals 182, it will happen by chance about 6.7% of the time. So it's not happening very often, but it didn't meet our definition of weird. Right? So it's unlikely to have happened by chance. It only happens by chance 6.72% of the time, but that's still not weird enough to meet our definition of weird. So in this case, when we decide whether we're going to reject the null hypothesis, which is our normal step 5, basically we reject the null hypothesis if our result is weird. If it falls out in those tiny places. In this case, doing the p-value method, it happens if the p-value is less than alpha. But for us, alpha was 0.05, and we just found the p-value was 0.0672, and it is not less than. So our result is not weird. It didn't quite meet that criteria, so don't reject H naught. So we reject the result if we fall out way out in the tails, pass into the regions we consider weird. That's when we reject the null hypothesis. But if our result doesn't fall in those weird regions, then we don't reject it. And here's a way to think about that, just conceptually again. The idea is, if we assume the average was 190 pounds, how weird would it be to have picked a group of 38 randomly selected males and gotten a weight of 182 pounds? Well, it turns out in this case, that would happen about 6.7% of the time. It's weird, but it doesn't meet our criteria of something having to happen less than 5% of the time by chance. And to relate it back to like a criminal trial, because that was brought up so many times, you can kind of think about it as like, you know, a crime scene in a sense, right? If you have one supposed eyewitness saying that this person committed the crime, then, you know, you have some evidence. But if you have, in this case, 38 people saying that you committed the crime, that's much stronger evidence. And that's essentially kind of what we're doing here. We're trying to consider how strong the evidence is. An example I gave some people the other day is, right, you see a person run out of a house where somebody's been murdered, they're covered in blood, holding a bloody knife, and they get into a car and speed off, right? What is the odds that that person, so let's assume that that person is innocent. What are the odds that that person would have been running out of the house carrying the knife, covered in blood, jumped into a car and sped off? Right? That's essentially what we're looking for here. We're trying to weigh how strong the evidence is. How likely would that have been to have happened by chance? How likely would it be to just be a coincidence that that person, maybe they ran in and got frightened and tried to revive the person and covered in blood, and they picked up the knife and for some reason thought it was a good thing to run off with that knife and jump in a car and drive away? How plausible is that to have happened, by chance, assuming the person was actually innocent? That's essentially the question that's being asked. So in our case, assuming the true average weight of New Mexicans is 190, how weird would it be to find a group of 38 people that only weighed 182 pounds? And in this case, it's weird, but not that weird. It happens about 6 or 7% of the time, which doesn't meet our criteria of having to happen less than 5% of the time for us to consider weird. So in this case, we're saying we have evidence. It's pretty strong, but it's not strong enough to definitively say, no, that's a weird result. We think that the null hypothesis is wrong, that males in New Mexico don't weigh 190 pounds. So basically, in this case, there is evidence, but it is insufficient. There's insufficient evidence. We do have evidence that New Mexican males weigh less than the national average, but it is insufficient. So we have insufficient evidence to suggest that New Mexico males weigh less than the national average. Any questions on that one? Let me do it on the calculator real quickly. So again, we can do this whole problem we just did with the tables instead, but we can do it on the calculator. This is, so go into my list of tests. Oops, don't need the second button. So go over to my list of tests, and this one is a simple z-test, so the first option. So this is on the calculator. This is a z-test. We can use it to get this number here. So on the calculator, we do z-test. It'll ask us if we want to use data or stats. In this case, all the stats were already computed for us, so we're using stats. I guarantee that's what I will give you on the real exam. I won't give you one with raw data. For us, the average value, according to the null hypothesis, was supposed to be 190, so that's what I'll put there, 190. The standard deviation was 27. The average that we found in our evidence was New Mexican males weighed 182 pounds. Our sample size was 38, and we did indeed have a two-tailed hypothesis, so I can leave that one as is, and now hit calculate. And when I hit calculate, it gives me the z-score that we found for our test statistic right here. Here's our test statistic, negative 1.83. It spits out that number for us. And then it also gives us the p-value, 0.067779, yada, yada, yada. So ours is slightly off from that, right? Using the table, differs in the third or fourth decimal place in this case. And that's because we had to round this number. In the calculator, it keeps all the decimals of this z-score when it finds the area to the left of it. Whereas in our table, we had to round to 2 decimals to use the table. So again, on the homework, they've been picky about that and they've marked you wrong if you use the wrong method. But on the exam, I'm not going to care. Either method is fine. So the z-test winds up giving us, it gives us both of these numbers. It gives us that number, and then it also gives us that the p-value is very close to this other number, whatever, 0.0677. Let's round that up to 78. So that's how you do this on the calculator. You still have to put all the pieces together. It just saves you from having to look stuff up in the table to find an area to the extreme in the side or in extreme sides of our test statistic, and it saves you from having to plug into this formula to find that test statistic. So it's ideal. If I was going to do this problem, I would do it on the calculator to get those values, and then I'd kind of come back and fill it in with all the remaining information. I do want to emphasize one more time, because this is a common mistake I see. People see the exam review, they see this picture with two tails drawn, and they just copy, and they always draw two tails. I only drew two tails because this is a two-tailed hypothesis. So I just want to reinforce that one more time. If it had been right-tailed, you would only see a drawing over in the right tail. If it had been left-tailed, you'd only see an area drawn over in the left tail. So just keep that in mind. Don't just, blindly copy and try to regurgitate what you saw in the exam review. Actually, if you can think about what the picture means, it makes these problems a lot easier. Okay. Any other questions? Or anything in general? Any bookkeeping stuff? There was a question I remember in the chat, which I've now closed. Let me open the chat again. About the type 2 error. So that was, I'm assuming, back when we were talking way up in the multiple choices that Jacob asked. Where was that? Number 4 here. So let me just come back and address this if you're interested in sticking around. So what would be a type 1 error versus type 2 error? I think the easiest way to do it is really go back and think of like the criminal trial thing. I should look it up so I draw it exactly the same way that I drew it there. I vaguely remember. I think this is how it went. Oh boy, maybe I should look it up so I don't draw it backwards and confuse you. But basically, we had a situation where I had a little like table like this. And if I remember correctly, I think I had it where this was correct. This was correct. So basically, we had H not true. No, it must have been. I'm trying to remember. Let me just do a new table. This may not match exactly the table that we had before. So let me just warn you with that. If you're trying to copy a table, either of them would be fine, but it just might look slightly different than the one that I did back then. So basically, the null hypothesis in reality can actually be true, or H naught can actually be false, right? This is the idea. They can actually be innocent, or they can actually be guilty. And then we have basically kind of over here our verdict. We can either reject H naught, or we can not reject it. So we don't accept it, but we just don't reject H naught. So basically, this is the equivalent. Rejecting H naught is the equivalent of a guilty verdict, and this is a not guilty. Oops, guilty. And the way that it works is, if the person is actually innocent and we said not guilty, that is a correct decision. So we've made the correct decision there. Similarly, if the person actually did the crime and we say guilty, that is also a correct decision. And in the problem that we just did over here in the multiple choice, we didn't reject it. So we said not guilty, and the fact of the matter was they were indeed innocent. So that was what we had over there. It was the correct decision. It was this case where they were actually innocent and we said not guilty. If you convict somebody who's innocent, that is a type 1 error. And then if you let go somebody who is actually guilty that did it, so if you let them go free, that is a type 2 error. So in this case, depending on how you want to think about it, sorry, try to zoom in so we can see them all at once here. Good enough. In this case, the second that we knew that the true value of mu was 56, which matched the assumption up here, right? We found out that our null hypothesis was indeed true. that narrows it down to these two things. We could have only had either a correct decision or type 1. The person was actually innocent in this case, in a sense. And so that takes you down to either a type 1 error or, or a correct decision. And so in this case, those are the two possibilities. If we had instead, how do we say it? So if this p-value had been smaller and we wound up rejecting the null hypothesis, so if this p-value had been like 0.02 or something, which was less than 0.05, then we would have rejected h naught, and even though h naught was true, and we would have made a type 1 error. So that's kind of the idea. This is pretty much guaranteed to come up somewhere in the multiple choice, one of these types of type 1, type 2 correct decision problems. So it's not worth a ton of points, but it's probably worth studying just so you can try to make sure you get that multiple choice problem correct. It's going to come up once or twice on the multiple choice. Cool. Cynthia, you asked a question again way long time ago. I think it was probably in relation to one of these problems. You said, could it be the same that if n decreases, then m increases? So that must have been in relation to this. Yes. So if your sample size got smaller and everything else was held the same, then that would make your margin of error bigger, right? So taking a bigger sample allows you to zero in better on the answer. But if you take a smaller sample, you're going to have to basically build your target bigger. You're zeroing out, I guess. Whatever the opposite of zeroing in is. So a smaller sample means that you're going to wind up with a larger margin of error. And again, you can see that mathematically. If I make n smaller, if I make the denominator smaller, so going this direction in the list from 4 to 3 to 2 to 1, the overall number is getting bigger. So absolutely, I think that's probably what your question was about. So otherwise, that should pretty much cover it. You should expect the real exam to look more or less like this format, more or less this length, similar types of problems, not identical, similar difficulty. And then you can expect one extra credit problem, which again will be from chapter 6. Any other questions, anybody? If not, then good luck. Let me know if anything pops up. Shoot me an email if you need a last-minute Zoom meeting. I can occasionally meet. I might have a little opening tomorrow to be able to meet, so send me an email if you want to try to fit in a quick Zoom meeting before you take the exam. But otherwise, good luck, and I'll see you guys at I guess the last exam review for the final exam is probably the next time I'll see most of you on a Zoom meeting. So cool. Well, then I'm going to end it.
Thank you.
Absolutely. Good luck, everybody. I hope this helped and cleared some stuff up for you.
I might have to email you to do a Zoom meeting.
Is that Cynthia? Is that you?
Yeah.
Okay. Yeah, sure. Shoot me an email. I might have some time like late afternoon tomorrow, possibly. So
Perfect. Okay. I have an English Zoom at like 2. So
cool. Maybe after that then. Yeah.
Okay. Sounds
Awesome.
good. I will email you.
Cool. Good luck, everybody.
You.
Take care.
Thanks.
Bye.